And previously you've used indicators, obviously, and you note that they change colour and they change the pH, but have you ever thought about how they actually work? Probably not. So they work actually by being a weak acid or a weak base. So because they're weak, what is a weak acid? Definition. Come on.
One with not much hydrogen around it.
No. No. I'm focusing on the weak bit.
It's not very strong.
Great. Anything else?
Something with a high pKa.
High pKa, low Ka, yeah, good. But
It's just else.
right, what happens to an acid in solution?
It dissociates.
It dissociates, but a weak acid only
Slightly dissociates.
partially dissociates. So a weak acid only partially dissociates. So when we're writing it, so let's say a weak acid, such as ethanoic acid. I mean, you should know it, it's not my fault. If I was writing an equation for the dissociation of ethanoic acid, which I've started to do on the board, which is frozen, how would I write that? How would I write it? That up there, corner.
What?
The dissociation of it.
CO minus plus H.
Yeah.
Dissociation is with the H.
Yeah, it's dissociating into its ions. Breaking up into its ions. But what about my arrow? It's reversible. So we've got a little equilibrium set up, and the same idea with weak bases. Weak bases only partially dissociate into their ions as well. So that's why we see an equilibrium set up. Okay, so our indicators work by being weak acids or weak indicators themselves. Okay, so have a look at the equilibrium for phenolphthalein here is our first example. Phenolphthalein is a weak acid. So do you remember when we were looking at weak acids? We can write its dissociation like this. So H plus and then your anion, which is how I've written it up here. Or you can write it as the reaction with water, because what we said was hydrogen ions don't really exist in solution. So we can write it as the reaction with water. So what do I produce on the other side? Plus my A minus, which is what I see here. So this is kind of just a general equation because we don't really need to know the actual formula for what phenolphthalein is. But this thing here, the undissociated acid, is colourless, and the anion gives us the pink colour of phenolphthalein. Anion is a negative ion. The anion gives us the pink colour on the right hand side of the equation. So this is all. Pardon?
It's not actually an ion at the start.
No, the A minus is the anion. At the at the start, it's undissociated acid, yeah, and this is the anion. Okay, so this is all thought about in terms of equilibrium changes and your Le Chatelier's principle. So if I add some acid in, so say you're doing a titration, and you start with alkali in your conical flask, and you add some acid in, right? What will happen is we'll increase the concentration of my H3O plus on the right hand side of the equation. Does that make sense? If I'm adding acid, that concentration is going to rise. So what will happen to my equilibrium? It'll shift to the left, which causes it to change to colourless. Yeah, it's going this way and it's colourless on the left hand side of the equation. So that's why when we're doing alkali in the conical flask, it's originally pink here. And then as we add acid, the equilibrium shifts to the left hand side and we produce a colourless solution at our equivalence point. We'll talk about that a bit more later. Okay. Whereas if you add your hydroxide ions, now it's not as simple as saying that the concentration on one side of the equation increases. With alkali, you need to think about what's actually going to happen. So when you've got a hydroxide ion, it's going to react with these H3O plus ions to give you water. So if it's reacting with the H3O plus ions, what's happening to their concentration?
Going down, you see.
It's going down because they're being removed from the solution. And so what happens to the equilibrium?
Just to the right hand side.
it shifts to the right hand side to replace those H3O plus ions that have been used up by the hydroxide ions. And so your solution changes colour to pink.
Somebody's going to clean the fire squad on Sunday.
Okay, so methyl orange is a similar idea. Here we've got the dissociation of our methyl orange, just represented generally by B for base, because methyl orange is a weak base rather than a weak acid. So again, a weak base is one which
Doesn't dissociate.
Oh,
Does dissociate.
Somewhere in between.
Partially dissociate.
Partially dissociates
So what's
it.
the difference between the both partially dissociate?
What?
There's also
This is a weak base.
what's the difference between the two?
One's a weak acid, one's a weak
Well, you're
base.
looking at the why they're weak.
Yes.
I wonder around one minor base.
Oh no. Why? Yes. What it means by the fact that they're weak. Okay, so this time it's dissociating. We're producing our hydroxide ions because alkalis produce hydroxide ions in solution. So that means our other ion has to be positive. The base part of it is actually positive. So the B plus ion gives us the orange-red colour, and the undissociated base gives us the yellow colour. So same idea. If you add alkali, you're increasing the concentration of your hydroxides on the right hand side of the equation. So what happens to your equilibrium? The equilibrium shifts to the left, and so your solution turns yellow. Okay. If you increase your concentration of acid, or if you add acid, again we need to have a little think about what's happening here. Make it orange. When you add in the acid, the H3O plus ions react with the hydroxide ions on the right hand side of the equation to give us water. So the hydroxide ions are essentially removed from the solution, so their concentration decreases. So what does the equilibrium do? What's the other way? It goes to the right hand side to replace these hydroxide ions that have been used up. And so that gives us our orange-red colour. Okay, so the next part of this topic that you may be asked an equation or a question on, sorry, what? Is the choice of indicators. So they may give you a table like this, maybe indicators that you're familiar with, maybe indicators that you're not familiar with. And they could ask you to choose a suitable indicator for a particular reaction. And it all depends when that colour change happens. So we kind of assume that that colour change happens exactly at pH 7 at neutral. But that's not the case. So all indicators will have a certain range of pH that they change colour in. And it all depends on their acid dissociation constant or their base dissociation constant. Pardon?
What colour is it before?
It's where it changes. It switches over.
So what colour is it?
So if you're going down the way, if you're getting more acidic, it'll turn to red at that point, yeah. And yeah. Okay, so it all depends on their acid dissociation constant or their base dissociation constant, remembering that indicators are really just... Yes, add one more word in front of that. Weak acids and bases. So they're all each indicator is going to have a Ka or a Kb value, depending on whether they're a weak acid or a weak base, and that will determine the pH that they change colour on. So let's have a look at ones that we are familiar with. Okay. So we're going to be talking about, and it will make a bit more sense when we have a look at these titration curves. The equivalence point, we did talk about this last year. Equivalence point is where that change in colour happens. And what happens there is there's a rapid change in pH during that equivalence point. And the equivalence point of your reaction will determine the indicator that you are supposed to use, because you need to have the colour change pH of your indicator to match up with the equivalence point. So say for example your equivalence point was between 5 and 8, right, for a certain reaction. Say that's your equivalence point was between pH 5 and pH 8. Can you see how methyl orange would not be suitable because it changes colour at pH 4? Yeah? So in fact, what would be suitable if you had an equivalence point between 5 and 8? Nope. Litmus, yeah. Litmus is the only one that changes during that equivalence point. So let's have a look at this first example.
Would you actually use litmus all the time? Looks like a pretty good one.
No, it's pretty rubbish.
Pretty good today. It changes like everything.
What?
But in terms of like equivalence point, all the time, work every time.
But each reaction will have a different equivalence point.
Alright, but like, it's only got 7. Like, I mean, more than likely it'll change every time.
Perhaps.
But no. You still understand, you know, you get a more better grasp of the topic.
Okay. Okay, so this first one we're doing with sodium hydroxide and hydrochloric acid. So sodium hydroxide is a strong base. For this you're going to need to know, have your head around what's a strong base, what's a strong alkali, or what's a strong acid from the name of it. So if you say that your acid is whatever acid, you should know whether that's a strong acid or a weak acid. You need to be at that stage by now. Okay, so when we have a strong acid and strong base, the equivalence point for this reaction happens, it's quite a broad range, between 2 and 12. So what indicators could we use?
All of them.
All of them. Why is that, Oisín?
Because they'll change the equivalence.
Yeah, they all change colour in the middle of the equivalence point. But phenolphthalein is also, or is most commonly used for that, because it gives the clearest colour change. Okay. Next example. Ammonia solution is a weak base, so you need to know that ammonia is a weak base. Your strong bases are the likes of your metal hydroxide, so potassium, sodium, whatever, hydroxide. And ammonia is a weak base. With hydrochloric acid, which is a strong acid,
All the questions. Like half the questions.
which are good practice. Okay. So my equivalence point is now between 2 and 9. So if you go back to your little table, pick an indicator.
Methyl orange.
Yeah, you've got methyl orange. Cool. Get the idea? I could keep going, but do you get the idea that the indicator needs to change colour? The pH range of the change of colour, of the indicator, needs to match up with the equivalence point of your reaction. Yeah, happy enough? Great. Just quickly though, to mention the last example there of ammonia and ethanoic acid, weak acid and a weak base. The pH changes so slowly with weak acid and weak base, and we'll see that with our graph. So actually there's no indicator that's really very suitable for a weak acid, weak base, and so we need to use a pH meter instead. Right, so we're going to look now at the idea of these titration curves. Flying on. Pardon? Oh, sorry. We're going to look at this idea of titration curves. And again, this is something, I don't know what it was with this topic in general, that I overcomplicated at school with these titration curves. We're going to work our way up to actually being able to draw these, which is very exciting. You've got a couple of options. When I was at school, I would have learned these titration curves. There's 4 types of them. But there's also, you can see that this is acid against base. If you do your titration the other way around, like base against acid, your curve is then the opposite way around. It will go down rather than up. So it's actually quite a lot to learn if you just learn these curves, but actually being able to interpret them, know what's going on with them in them, is actually a lot more important, I would believe. So let's have a look at them and what we can see from them. Okay, so okay, so right, there's what? Okay, so there's 3 bits of information that we can tell from our titration curve automatically. First thing is from your starting point. Your starting point tells you the pH.
I have a message from Ronan. Could be important.
Could be, might not be. The starting pH tells you the pH of the acid. Why does it tell me the pH of the original acid?
You have initially in it.
Yeah. But what's the volume of base that I've added at the y-axis? Pardon? No.
What's up to you? Whatever you have as. 0.
0, yeah. So, what?
How can you have a concentration but nothing? Or no?
Okay, so imagine what's happening here. You should have got props. But you've got a conical flask in it. Can you remember doing titrations? You've got a conical flask. Oh, gosh. You've got a conical flask, yes? So you've got your conical flask and you've got either an acid or an alkali to start with, right? And then in your burette you have the opposite solution. So if you've got an acid in your conical flask, you've got alkali in your burette. Okay, that's what we're looking at, these ones here, the acid versus base ones. Okay, so you've got acid in your conical flask, right? And I've got a base or an alkali in my burette. So the initial concentration before I add anything from my burette is going to give me the concentration of what? Oh my. Conical flask.
Yeah,
this is a mess, I'm sorry.
Actually,
You need a stumper either.
you did.
Come on, Rudosh. I didn't even have one.
Wait,
You
see,
probably got it.
first.
Right. Picture diagram is now on the board. Yes? Okay. So I am. Imagine this little probe.
Oh, thank you.
Imagine this little probe that I've done is measuring the pH. Okay? When I've added no alkali, 0 centimeters cubed, no volume of alkali, what will my pH tell me?
The acidity of what you have.
But what do I have?
An acid.
Yeah, okay,
A
so
weak acid.
maybe or maybe not. Okay, so when I've added no alkali, the pH of the solution is going to tell me the pH of the acid.
Yes.
Yeah?
Yes.
Because I haven't had any alkali. That's where we were trying to get there.
I have a question.
Yeah.
How can you have a pH of anything if you have nothing?
So I do have something. I have something.
Your volume thing you're titrating. Oh, your volume is your volume of base.
Yes, that I've added.
So
what's going along
acid there now?
Yes. So what's going along the x-axis is how much alkali I've added from my burette. Come on.
Does the base not need to be above 7?
What?
Does the base not need to be above 7?
What base?
The base has
No,
it.
no. Look at the.
No, that's what I mean, but I thought a base had to be above 7.
Yes, but look at. Could you please? You better not have you buy me a new one.
For base, you don't have to be last one.
Yes, yes.
So you should not be above 7. So I think you're wrong with base being until it's above 7.
Oh, because the base doesn't exist at this point. It's at like 1 pH.
Yeah. So what's going along my x-axis is the volume of the base that I have added.
Sure, you don't have a base until it's plus 7.
You haven't added base yet.
Yeah.
Well,
So
I've got 25 volumes.
Because you've got your titrating against something. You've already got an acid in the conical flask at the bottom.
Oh, she's trying to make
Base
the
is
raw.
only your
I'm trying to make the raw yolk.
Yes.
Like a base.
yeah. Just let me.
Oh, I get what's on that.
Okay. So the diagram I have at the side is the titration. Yes.
Oh, I think.
So when I've added no base, it's going to be totally the concentration of the pH of my acid, my original acid. But as I add some of my alkali, the pH is going to rise and rise and rise, which you can see is happening. Yeah? Okay, good. So that's the first thing we can get is the pH of the original acid. So from that I can tell whether it's a strong acid or a weak acid, because that point where it crosses the y-axis tells me the pH of the acid. So what is the pH of my acid in this first one? 1. So acid equals pH 1. Is that a strong acid or a weak acid?
Strong.
It's a strong acid. So this titration is involving a strong acid. Yes? Okay, great. Second bit of information is this equivalence point. Okay, what do you notice about the equivalence point?
Straight.
Yes, good. So what happens, equivalence point is when you've got a rapid change in pH, and that's the change where your colour change is going to happen in your indicator. What does that allow me to do, that equivalence point? Yeah, so that part of the graph allows me to choose what indicator I'm going to use. Okay? And then finally, the information that I can get from this is, at the equivalence point, what is the volume of alkali that I've added? So that is when we were doing our titration calculations from our practical method. So we would have noted down the volume from the burette once the colour change happened, at the exact change of the colour point, or the colour change. That's the same thing. If we were to draw a graph of what we were doing, that is the volume that it would read on the burette at the time of the colour change. So what we can use from this curve is actually we can do a full titration calculation, because the volume that we've added at the equivalence point is the volume that would have been added at the colour change, and so we can work out the concentration, blah blah blah. All very exciting. So those are the three pieces of information that you can get from it. Little mistake you should adjust is that should say the equivalence point is between pH 3 and pH 10, not pH 120. I think it said 12 and then I changed it to 10, and obviously forgot to take the 2 out, so you need to make that change. Okay, so let's have a look at the second curve. So remember, the first bit of information we can tell is the pH of the initial acid. So this is now, it starts at pH 3. What's pH 3? It is an acid, yep. It's strongish, but we're going to go with it's weak. Because it's weaker than 1. Well, I actually think in your breakdown of it, I think it's 0 to 2 is strong and 3 to 6 is weak. I'll check my GCSE notes, but I think that's what you learn. Maybe. Yeah. So now I can tell that I'm starting with a weak acid. Okay, equivalence point you can see is shorter this time. Okay, and it happens between pH 6 and pH 10, so again we can choose our indicator based on that. And then if we want to do a titration calculation, we just work out the volume that was added at the equivalence point. Simple. So you can see how the shape of that is slightly different. And you can see how it's all kind of shifted up a wee bit, because we're not using a strong acid now, we're using a weak acid, so the pH of everything is a little bit higher, because it's less strong of an acid. Okay, moving down to curve 3, you can see now where have we started, pH 1. So this is a
Strong.
This is a strong acid, good. Okay, and there's your equivalence point, and it happens between pH 3 and pH 8, so you can choose your indicator accordingly. However, your final pH of your solution also gives you an idea of the pH of the alkali. So what can I tell about my alkali from this? It's weak. Why? Because it's only 9. Yeah, pardon? Oh well, it's probably like 10. Yeah, so but it's still pretty weak. Okay, and then finally curve 4 is where we start at pH 3, so this is a weak acid. Okay, and what do you notice about the equivalence point? It's small, and it's also, there's no actual completely straight bit of it. And do you remember how we talked about in the previous page that weak acid versus weak base, there's not much of an equivalence point, so there's no suitable indicator, and that's why we need to use a pH meter, because there's no well-defined point where it's going to change. And again, the final pH of your base will give you an idea of the strength of your base, which is pH 10, so that is a weak base. And if you compare that up to the previous two, you can see how the final pH of your base was pH 13, which is pretty strong for both of those. And so that's a strong alkali. So there's loads you can tell from a titration curve, and I think it's best if you can interpret it rather than learn those. But you can sit and learn the shape of those. So look how the first one, strong acid, strong base, that's where you've got your longest equivalence point, and it starts at the lowest pH and it ends at the highest pH. And so you can learn them if you want, or be able to interpret them. So what we want to do now is put that into words, actually, and what can we tell from these 4 curves. So we've done it there for curve 1. We've said the inflection point or the equivalence point, doesn't really matter, they're both the same thing. Curves between pH 3 and pH 10, and this is indicative of a strong acid, strong base titration. And the initial pH of the acid is 1, which would suggest a strong acid. So we want to do that for the other 3 curves. You could be asked to do this in an exam, but what can you interpret from it? Okay, so have a look at curve 2 there. What we're going to do is write a similar answer for each of these. Okay, so this time the inflection point, or the equivalence point, whatever you prefer, occurs between. What does it occur between? If you look directly at the vertical bit, I can see how it starts to change at 5, but can you see how the vertical bit starts at? It's like 6.5. We'll go with 6.5. I know it does say 6, so we'll go with 6. Between 6 and 10.
Yeah, it's that one.
Okay.
Did the note say 6?
Yeah.
Just mess up everything.
Yeah.
Yeah.
Okay. So basically, this will give you, the first number will give you an idea of the strength of the acid. Second number will give you an idea of the strength of the base.
Are you alright then?
Okay. So this is, oh, we've gone purple. Of a weak acid, strong base titration. And then the initial pH of the acid is 3, which would suggest a weak acid. Okay, keep going for 3 and 4. So let's have a look at how we would actually sketch one of these curves, which would be really fun if you were asked to do that in the exam. So we'll have a look at what you're given in a typical question in a second. Okay, so you will be able to work out from your equation, pH equals minus log H plus, you'll be able to work out the initial concentration of your acid. Okay, then from the names of your acids and base, you should be able to determine whether that's a strong acid or a weak acid, or a strong base or a weak base, and that will give you an idea of the length of your equivalence point or your inflection point. So that if you've got strong acid, strong base, that's going to be the longest, and so on. Okay, and then you will be given. It'll go between 2 specific points. It'll go as in roughly between the points that you've got on your previous page. So between 3 and 10 of a strong acid, strong base, 6 and 10 weak acid, strong base, and so on. Okay, so easiest way to look is just have a look at an example. Okay, so flick over to page 51, and you're told that you have 25 centimetres cubed of 0.1 molar hydrochloric acid. And you have and you have 0.2 moles or mole per decimeter cubed of sodium hydroxide solution. So basically, if you think about what's happening here, you've got your hydrochloric acid in here in the conical flask, and then in your burette, you have your sodium hydroxide solution. So just as we did before, you're doing a titration until you're adding sodium hydroxide until the colour change happens, and you're noting the volume at which it happens at. Although they don't give us the volume, but we can calculate it, which is very exciting. Okay? Okay, so the first thing you want to work out is your initial pH of your acid, because that tells you where you start your curve. Okay? So we've got hydrochloric acid here. So what's our equation for calculating pH? Always. Okay, so what I want you to be thinking of is, how can I calculate pH? Well, that's the only way I can calculate pH. So whatever I have, I need to try and, if I have hydroxide ions, I need to try and get hydrogen ions, because that's this, I need the concentration of the hydrogen ions in order to be able to work out the initial pH. So, we've got hydrochloric acid, and what does that dissociate into, please? Cl minus. Okay, the importance of doing that is because in case you had a dibasic acid like sulfuric acid, in which case you would have 2 hydrogen ions produced per molecule of sulfuric acid. But we've got hydrochloric acid, so if we have 0.1 moles per decimeter cubed of our hydrochloric acid, our ratio is 1 to 1. So what's the concentration of our hydrogen ions going to be? 0.1. Okay, then I can work out my initial pH by doing pH equals minus log H plus, which is equal to minus log of 0.1, which if you put that into your calculator, Kiva, gets you a pH of 1. So I now know where I'm going to start my curve on my titration curve. Really exciting. Okay, so the shape we need to be thinking about whether I have a strong or weak acid and a strong or weak base. I need to decide the strength of my acid and my base. So, first of all, I've got hydrochloric acid. Is that strong or weak?
Strong.
So I've got strong acid. And then I'm titrating it against sodium hydroxide solution. Is that strong or weak? Strong base. Okay, so what I want just to write in here is that shape will be like which curve?
1.
Good job. Equivalence point. I don't think that's how you spell equivalence, is it? That is. Equivalence point between roughly
3 and 10.
approximately 3 and 10. You're lapping this up.
Yeah.
Must be no runner.
I don't know who said you, I think.
Yeah. Okay, volume of base then. So that's going to tell us the length of our straight part of our curve. Okay, and then finally we can work out the volume of base, which will tell us where our equivalence point actually happens along our x-axis. So for this we need to think about what's happening here. We're titrating hydrochloric acid against sodium hydroxide. Finish that equation for me.
H2O plus NaCl.
Good, NaCl plus H2O. It's already balanced, so it's all good. Okay. First of all, I need to work out the number of moles of my hydrochloric acid that I have present in my conical flask. How do I do that? Come on.
N equals CV.
N equals CV, yep, good. So the concentration of your hydrochloric acid is 0.1. And the volume of hydrochloric acid that you have is 25 centimetres cubed. So 25 centimetres cubed is how many decimeter cubed? 0.025, or you can just put it into your equation as 25 over 1,000, whatever you prefer. I'm just going to put it in as 0.025, if that's okay. And that's going to give me 0.0025 moles. Okay, bring that over to your sodium hydroxide to work out how many moles of it I have. It's a 1-to-1 ratio. And so it's going to take 0.0025 moles of sodium hydroxide to neutralise my hydrochloric acid. I'm interested in the volume of sodium hydroxide that I need to add. So rearranging that equation, what does volume equal? Good, N over C. So 0.0025 over your concentration, which is, from the question, is 0.2 molar sodium hydroxide. And that gets you a volume of 0.0125 decimeters cubed. What probably want to convert that into? Centimeters cubed.
Why would you convert 25 centimeters cubed in the first place?
Because it needs to be in decimeters cubed to use that equation, just in case we ended up. Well, as long as you remember on the other side that it's still in centimeters cubed. Times by 1,000, that gets us 12.5 centimeters cubed. So that is the volume of base that your inflection point is going to happen at. So taking all of that information, are you ready to plot this curve?
You're just going to come back.
No. Okay, so initial pH is what? 1, because that's the initial pH of our acid. So it's going to start here. So we said, what did we work out in the last point? The equivalence point is going to happen, or colour change is going to happen at 12.5 centimetres cubed of sodium hydroxide. That is halfway between 10 and 15. So our equivalence point is going to happen at this point. Where did we say the equivalence point is between, pH-wise? 3 and 10. So we go up here until we get to 3. That's where your equivalence point is going to start. Keep going up. Well, actually, you can do that as a solid line because that's going to be your straight part of it. It's going to stop at pH 10 and then it's going to curve round again. Are you ready?
Where does it curve around this?
Roughly sort of 12, 13. Okay. So it goes, actually make it more curvy than that. Something like that. And then there's your equivalence point. And then up to something like that. In fact, if you really wanted, because you were given the concentration of your sodium hydroxide, you could work out the solution of your, the pH of your sodium hydroxide by working out the concentration of your hydroxide ions. I'll keep talking, you can leave if you want. 1-to-1 ratio, but I'm recording, so we'll keep going. So that gives you 0.2 moles per decimeter cubed of your hydroxide ions. So then you can just use kW to get the concentration of your H+. See you later. 1 times 10 to the minus 14 is going to be your H+ times 0.2. H+ will equal, it's going to be 5 times 10 to the minus 14. pH equals minus log of H+, which is equal to 13.3. So that's where you want to finish your, whoa, crazy. Let's do the second example, where we now have sulfuric acid titrating against ammonia. Right. So the first thing we can work out is our initial pH of our acid. So again, the acid is going to be in the conical flask. In here you're going to have your H2SO4, in your briarette you're going to have your ammonia solution. Oh no. Oh no. I don't know what happened there. Ammonia solution. So as you add the ammonia, obviously the pH is going to rise. But we want to work out a particular value so we can sketch our curve. So initial pH, this is where you need to be a little bit careful because you've got sulfuric acid this time, which is H2SO4, which dissociates to give us how many hydrogen ions? 2. And then your sulfate ion. So yes, the concentration of my sulfuric acid is 0.25 moles per decimeter cubed, but my ratio is 1:2, so that means the concentration of hydrogen ions in solution is going to be 0.5 moles per decimeter cubed. What do I do with that value?
You use it for you put it in the minus log.
Good. pH equals minus log concentration of your H plus ions, which is minus log 0.5, which works out as 0.3. I don't know where that 0.3. Don't know why I actually got by accident. Okay, shape we get from the name of our acids, deciding whether they're strong or weak acid or strong or weak base. So sulfuric acid, strong or weak? Okay, so we've got strong acid versus ammonia, which is weak base. Okay, so it's going to be shape like curve which? Have a look back to page 48.
Not just cartoon.
Curve 3, yep. It's going to be shaped like curve 3. And so your equivalence point is going to be roughly between pH 3, because we've got a strong acid, and pH 8, because we've got a weak base. Okay, so that's going to give us the length of our vertical part of our section of our graph. Okay, volume of the base, we need to write our equation for what's happening in our titration here first of all. What do we get when we react sulfuric acid with ammonia?
Ammonium sulfate.
Ammonium sulfate, fantastic.
Is that means a strong acid weak base?
Yep. Strong weak base. You're horrible. Okay, great. Ammonium sulfate is what we're going to produce. And go one step further and tell me the formula of it. What's the charge on an ammonium ion?
Plus.
Yep, NH4 plus, yeah. So it has a valency of 1. Sulfate has a valency of 2. So when we swap and drop that, I need to put the ammonium in brackets.
Isn't that ammonia?
Yes, but the salt you produce is ammonium sulfate. So if you want to write a word equation, sulfuric acid plus ammonia gives us ammonium sulfate and no water or anything like that. Okay, so you've got your H2SO4 reacting with ammonia, which is NH3, to give us ammonium sulfate, whose formula we just worked out. Okay, is that balanced?
No.
No, so what do I need to do? Yep, how do I do that? Yep, just shove a 2 in there and that's us balanced. Okay, so I can work out the number of moles of sulfuric acid because I have a volume and I have a concentration. So N equals CV, which is 0.25 times the volume, which is 25 over 1,000, or if you prefer to work it out first, it's 0.025. That gives you a number of moles of 0.00625. Okay, and I want to work out how many moles of ammonia would react with that. So bring it over to my ammonia. What's my ratio? 1 to 2. Okay, so it's going to react with 0.0125. Oh. Okay, and then I can work out the volume of ammonia. So I know where to put my equivalence point by doing number of moles over concentration. So number of moles is 0.0125. Concentration of my ammonia is 0.5 from the question, which is 0.025 decimeters cubed. Times that by 1,000 is 25 centimeters cubed. So what that tells me is the volume of base where my equivalence point happens. The volume of base at which my equivalence point happens. So let's put that all into our curve. first bit of information we worked out was that the initial pH of our acid is 0.3. So it's going to be fairly low down here. Okay, if you want to take a ruler and work it out accurately, you can. Okay, in an exam I would advise you do that. Your equivalence point is going to happen at 25 centimetres cubed of ammonia, so you could put a dotted line all the way up from 25. Okay, we said the equivalence point was going to be between pH 3, so we write point here, and pH 8, so that's going to be the vertical section of our graph. And then we just join the dots, make the curve, again make that a wee bit curvier. Okay, and it's a weak base, so you want to level it off about pH 10 or so.
How do you know where to level it off?
Well, again, so ammonia is a weak base, so it's not going to go up to 14. Because ammonia doesn't have a pH of 14, it's a weak base, so it's going to have a pH of really between 8 and 10. So probably it should level off a wee bit sooner than that. But go for something between 9 and 10, I'd say, if it's a weak base. If it's a strong base, you want to level it off between maybe 12 and 13. So just, you can write that down, even weak base. Between 9 and 10-ish. So then strong, you can write strong base between 12 and 13-ish. Or if you want to go and work out concentration of your hydroxide ions and work out the pH, you can do that. Just to mention, you could actually be given a titration or asked to draw a titration curve for the other way around. It's less likely, but you could be asked to draw a titration curve. Are you done with that page?
No.
You're asked to draw a titration curve for where you would have your alkali.
Are we gonna have to remember what curve is between?
So, yeah, I would learn your equivalence point values, just those ranges, like, well, it's really just either 3 to 10 or 3 to 8, or what's the other one, 6 to 10, or 6, or then there's not really one for, but otherwise, yeah, so some people will learn those curves all off, but I prefer just to interpret them. Okay, so you may be asked where you've got the alkali in the conical flask, the acid in the burette. So this time your titration curve will look like this. This is actually important. Okay, so your pH is still going to be on your y-axis, but what's going to be on your x-axis now? No. Volume of acid added. Yes. Okay, so you're starting with an alkali in here, and again, imagine I had a pH meter in here, and you may be given the concentration, in which case you would have to use your kW to work out the initial of it. Blah blah blah. I don't think they would ask you to do this. It's more recognising a curve that it's this way round. So as you said, Oisin, let's say this is 7, this is like 4. It's a terrible graph. Okay, so say it's a strong base. It's going to start up here. And then, are you happy enough that as we add acid, what's going to happen to the pH?
It will go down.
It will go down, because the lower the pH, the more acidic. So say it was strong acid, strong base, it's going to be between 3 and 10, your equivalence point.
You're right, this somewhere.
You can do if you want. Okay, so it's going to be shaped something like that.
An inverted sigmoidal curve.
Yeah. So basically, all I'm saying here is you need to just be aware, if volume of acid is on the x-axis, your curve's going to be the other way around. It's going to start high and then it's going to decrease. So just being able to recognise that, I guess. Is that okay? An example of that appears on page 56, question 4. You can see titration curve A. Oh, well actually that's the question, but you can see they're different shapes, so you can at some stage interpret them. Is that okay? So the theory of buffers can be quite complicated, and honestly I think it was this topic, again, overcomplicated this myself at school, so don't do that. The two main areas of buffers that you would get questions on are 1, explaining how a particular buffer works, and 2, a calculation on buffers. Talking to people in general across A-level chemistry, buffer calculations, they say, are the worst. But they're not. They're not. We're going.
Because you said none of them were the worst. So like,
None of them are the worst. Maybe it's the worst, but we are going to tackle it head on, and we're gonna conquer them. Okay. So let's have a look first of all at the theory of buffers and how they work. So buffer by definition. I think this is your this is your C definition. It's a solution which resists changes in pH on addition of small amounts of acid or alkali. So if you have a solution and you add a bit of acid or alkali, the buffer works to try and maintain the pH.
How do you know when to write base and when to write alkali?
So a base by definition is something that will neutralise an acid to give a salt and water only. An alkali is a soluble base. So something you can make a solution of. Here, you can always use alkali if you want, because it has to be in solution.
If you're a base instead of alkali, you just put them on.
Yeah, be fine.
You know that water can have both. How do you know which one it is? Like, there's a question into like pick which one.
So the basic thing that you need to know is that a buffer in chemistry is a weak acid and the salt of that weak acid. Where is a buffer important in our body? In your blood, why?
Maintain pH.
Why?
But if I just had a glove for one night, you'd be done for it, would you?
To make sure that the proteins in the red blood cells don't denature.
Yeah, but what makes your blood acidic?
Alcohol.
Oh, does it? Okay.
The blood will maintain like 7.25 pH or something.
Is it not slightly acidic? Well, I don't know. Maybe. I don't know.
Because if it was acidic, it was.
But if you have more carbon dioxide in your cells, does that not make your blood?
Makes more sense.
Yeah, so that's what it's got for. But so you need a buffer in there to maintain your pH. Cool. Okay, so if you're given a particular buffer, you need to be able to write equations for it, and you need to be able to explain how it works.
Alcohol does make your blood acidic.
Okay, great. Thank you. I wasn't like
No, you don't know.
I wasn't questioning you. I just
Just a wee fun fact.
didn't know. Yeah, I just didn't know.
That's verified.
It's verified by Wikipedia or something. Okay, so best looked at in terms of an example and what is actually happening in this. So what we've got here is ethanoic acid, which is a...
Acid.
Yep, it is.
Weak.
It's a weak acid. And in the buffer system, we also have sodium ethanoate, which is the
Strong.
the
Conjugate.
salt of the weak acid. It's the salt. So here we've got a weak acid, ethanoic acid, and the salt of the weak acid, so sodium ethanoate. Okay, so starting off first of all with your weak acid. Weak acid means that it
Dissociates.
Only partially dissociates.
partially dissociates, so we read it as an equilibrium reversible reaction. What we're going to do, because it is a weak acid, helpful noise disturbance. Because it's a weak acid,
Brendan will love it.
because it's a weak acid.
But you know about.
Right, so when the ethanoic acid dissociates, it only does so partially. That's why we've drawn the little forward arrow as short. The reverse reaction as longer. So what you're left with is what we call a large reservoir of undissociated ethanoic acid. Because it only partially dissociates, we have this like pool of ethanoic acid that is ready to dissociate if it so needs to. What would cause it to dissociate a little bit more? Look at your equilibrium.
Temperature. More ethanoic acid.
Well, yeah, it depends whether it's exothermic or endothermic, but yeah, possibly. More what? Yeah, if you produce more acid, okay, what else could you do? You're changing the pH of the system.
Yeah.
Nope.
You make a wee OH or something.
If you make a wee OH, because why? What will that do? Look at this equilibrium right here.
Just gonna move the equilibrium to the left if you make an OH.
No, it won't actually. Come on, think. We're thinking about changes in pH. No, because you need to think about this.
Put in a buffer.
What would cause this equilibrium in the blue box to shift to the right?
I don't know.
You should know.
Increase concentration.
Pardon?
Add an extra hydrogen.
So adding an extra hydrogen, that's going to shift it to the left to try and remove it.
Add OH, it's going to create water
Keep
on
it
the
on
side,
the
so
So which would do what?
remove the H plus ion.
Yeah, okay. So if you have a hydroxide ion, say for example, all I was really looking for is something like decrease of concentration of your H+, but this is good. If we have hydroxide ions, they'll react with the hydrogen ions to produce water.
Mister, are you getting more than metabolic or what?
Oh, yeah, we really did. Okay, so effectively I'm removing the H+ from the system. So if I removed H+ from the system, that would cause the ethanoic acid to dissociate a little bit more. So the point of that was the ethanoic acid is ready to dissociate. If we added in an alkali, for example. But we'll get there. I'm just saying that equilibrium's there, ready to be shifted. Okay, so my buffer system works by having this reservoir, let's pick a different colour, reservoir of my undissociated acid, and these ethanoate ions, because the salt of the weak acid, sodium ethanoate, because it is made up of these ions. Because it's made up of those ions, it will fully dissolve in water to give you your ethanoate ions and your sodium ions. So you'll have your ethanoate ions, which are ready there to be in action for the buffer. And you're also your undissociated acid. Let's very quickly look at this. So remember, the core aim of this buffer is to maintain pH, or maintain the pH if you add in some acid or some alkali. So if I add in some acid, you're going to increase the concentration of your hydrogen ions. Yes? What will that have the effect of doing? Yeah, shift the equilibrium to the left hand side.
You're what? You're adding acid. But
It would shift it to the left hand side, but what I want my buffer to do,
why?
if you increase the concentration of H+, if you increase the concentration,
Is that not acid there? Ethanoic acid.
it is, but that's the undissociated stuff. No, if you add in any acid, like say hydrochloric acid or something like that. Yeah, H+ in general. But I want my buffer to be able to remove those extra H+ ions. So I'm looking for something within my two equations there that's going to remove the H+. And the thing that's going to remove that is your ethanoate ions, which yes is essentially the equilibrium shifting to the left hand side. You've got your ethanoate ions reacting with the extra H+ ions to shift to the left hand side. But in reality, because this only partially dissociates, or ethanoic acid, because it only partially dissociates, most of the ethanoate ions actually come from the salt of your weak acid. But anyway, either way, they react with the H+ ions to produce some more undissociated ethanoic acid. So essentially the H plus ions are removed, and that maintains your pH. Okay, so over on the next page, I'm just going to stay on this page to show you what happens. Although we've already really talked about it. If you add in more alkali, you're going to be adding in hydroxide ions. And if I want to get rid of them, what will happen is those hydroxide ions will react with the H plus ions that are here on your right hand side. So you always want to be looking at your equations. They react with your H plus ions, essentially removing them from the system. So in order to maintain the pH, my equilibrium just shifts to the right hand side. So more of my ethanoic acid dissociates to replace those H plus ions that have been lost. And you maintain your pH.
Yes.
Job done. So the thing is, write your two equations and then literally work out what could I do to either remove the extra H plus ions, or to create more of them if I've added an alkali and I've got rid of some of them. We'll look at a couple more examples tomorrow.